По-английски.
Okay.
I'm glad to introduce our today's speaker, Georgy Sharygin. This is a talk together with Dmitry Gurevich and Pavel Saponov.
Yeah, Sharygin is also participating in our work. Yeah. Who's my postgraduate student, Misusha, over there.
Okay. And the title is Operations on Universal Enveloping Algebras and the Argument Shift Method. Yes. Гош, значит, нужно...
Почему вы, так сказать, говорите на импортном языке?
Потому что очень много иностранных слушателей.
Да.
Значит, Гоша, нужно сделать так. Можно.
Вместе со мной или же?
Так, нужно как-то... Вот этот микрофон.
Okay. Okay, shall I begin?
Yes.
Okay, so just this is a report on what I would say, what I call a work in progress, and I expect that Dmitry Ilyich will be making lots of comments on my talk, but yeah, so it will actually be a kind of joint talk in this case, in this sense. Yeah, I'll begin with some very classical theory, a very simple theory. So suppose we have a Poisson manifold, that is to say, a smooth manifold M, and a Poisson bivector on it, Poisson structure. So Poisson structure is a bivector field, intersection of the exterior square of the tangent bundle, not cotangent, but tangent bundle of M. And the only condition that we have is that its Houghton bracket with itself vanishes. This is equivalent to say that we have a Poisson bracket M on the functions on M, which verifies the Jacobi identity. This equation is equivalent to Jacobi identity, in fact. This is a classical result, so I'm not going to explain this. Now, when you have such structure, it is a classical question how many commutative subalgebras there are inside the Lie algebra of functions with respect to the Poisson bracket. There are lots of different ways to construct such commutative subalgebras. They are all very important in various classical problems, because commutative subalgebras in Poisson algebras correspond to various integrable systems. So just finding new examples of commutative subalgebras is already quite a big question and quite a renowned one. And among many various constructions that produce such commutative subalgebras, there is one which I love, which I like, which is particularly simple, and which I am going to explain in a very few words right now. This is what we call the argument shift method. Suppose we have a vector field psi on M. Then taking its Houghton bracket with pi, we obtain what is called the Lie derivative of pi with respect to psi. One calls a vector field Poisson vector field if this is equal to 0. In this case, there is nothing interesting because Poisson vector field is just kind of symmetry of Poisson structure. What we're interested in, it is the next best case, next best situation. It is when, although L of psi is not equal to 0, but the second Poisson derivative of pi with respect to the same vector field vanishes. In this case, one has the following very nice construction to obtain lots of commutative elements in the Poisson Lie algebra. The Lie algebra of functions with respect to the Poisson structure. Namely, let f and g be Casimir functions. That is to say, functions which commute with everything. And the same with G. And we can take the derivative with respect to the Poisson, to the vector field psi. And since if psi were Poisson vector field, then this derivative will still be in the center. But since psi is not Poisson, but only verifies this condition, which is sometimes called Nienhuis condition, this derivative is not in the center. Sorry, that's my, I need to mute it. Sorry, I need to mute my. Okay, I hope it was muted now. Okay, so it is not in the center, in the Poisson center of this algebra. And if we do the same thing with G, it is not in the center again, but still they commute.
I'm sorry, can you repeat again? Because
Yeah. So we have two elements in the two Casimir functions. It is elements of the center of the Poisson Lie algebra.
yes.
Then you take the derivations in the direction of the vector field psi, which verifies Nienhuis condition. And what you obtain will not be central functions anymore, but they'll still commute with each other, not with everything, but just with each other. And this is very simple. This is very easy to prove. This is pure algebra. So I'm going to spend 5 minutes proving this. So you do the following trick. You take the identity f g equal to 0. They're both Casimir, so this is equal to 0, of course, right? And differentiate it with respect to psi. It is still 0, of course, right? But now this is equal to psi of f g plus f psi of g plus f g sub psi. So where this is the Poisson bracket with respect to the derivation of the Poisson bivector. You can obtain new bracket with respect to this bivector. which is non-zero. Now this term is equal to 0 because f is in the center, as well as this one. So what you obtain is this identity. Now you take this element, and this element, and apply psi to these three identities again. What you obtain will be three identities of the same sort. So for instance, if you apply it here, you will get 0 equal to psi square f g plus f, sorry, psi f psi g plus psi f g psi. The second one will give psi f psi g plus f psi square g plus f psi g sub psi, right? And finally, if you apply the same result here,
Could you explain what does it mean this notation, the bracket?
this is a bracket with respect to this bivector. You have another bivector, L psi of pi. It is again a bivector field. So you can obtain a binary operation with respect to this bivector.
Is it Poissonian?
In this case, it is Poisson. In this case, it's actually a variant of what they call Leonard-Magritte induction, but without assumption that one of these bivector fields is invertible. There is no assumption of this sort.
In the same space, we have two brackets.
Yeah, actually, it is by Hamiltonian structure.
So there's your pencil, you have pencil.
Sorry?
You have your pencil bracket.
Yeah. These brackets are matched pair of brackets.
But is it when you say about Dutch bracket? Okay, how you pronounce Nieuwenhuis?
Nienhuis.
Nieuwenhuis. It's related Nieuwenhuis with Dutch bracket or no?
Yes, it is this.
It's just related with Dutch bracket with Nieuwenhuis bracket.
Yeah, it is. It is the guy who invented these Nienhuis brackets. If I understood you correctly.
Just incidentally.
Yes. Arnold's principle does not apply here. Okay, and then we apply the same trick.
So you have the second identity.
You just take to this. Yeah.
I'm sorry, my question is back up. Can you explain this bracket in terms of Nieuwenhuis bracket or no? Or
Which one?
The construction which you construct.
Okay, f g sub psi is equal to L psi pi applied to the f dg. Like this. No, just this.
Where alpha,
This is d differential. df dg.
This is L.
L, yeah, it is L.
It is on one form. It is super. It is bracket on one form.
No. It's just by vector field, and we can couple it with
Sorry.
two one forms. Okay. So let's go on. So now I take the third element here and do the same trick here. It is equal to 0. Now I have psi f g sub psi plus f psi of f sub psi of g sub psi. And the third term is equal to 0 because if we apply psi twice to the bivector, we obtain 0. Now, if I take the so this element vanishes because g is in the center, as well as this one. Now we take the sum of the first and the second lines. We get twice psi f psi g plus this and this, but it will be equal to the third line. So we get that this is equal to 0. Just this. Actually, by induction, you can now show. So induction, you now show that for every p and q for every non-negative integers. For every two non-negative integers p and q, the commutator of psi applied p times to f commute with psi applied q times to g. So this gives us a very large family, but well, potentially a large family. Yeah, f and g are still in the center.
No, I mean,
For any two elements in the center, this will commute. So this gives us
also elements psi to the power p of f and psi to the power q of f.
yeah, sure, it is a particular case. P can f can be equal to g. It is also possible. Yeah. So this gives us a very large family, potentially very large family of commutative elements inside C of inside the functions of on manifold. And as you see, this method is pretty simple. It's just induction on number of times we apply psi to f and g using this formula, and that's all. Because actually, well, when we shift argument along in the direction of vector field psi, the first term in Taylor decomposition of the shift will be equal to the derivative of f in direction of psi. That's why they call it argument shift method. Yeah, and here is a particular case which will probably explain this name even better than what I have just done, because this method was first formulated and totally understood in a very particular case of Lie algebras. Namely, assume that M is equal to the dual space of Lie algebra. Then there is a canonical Poisson structure on M, which you can assume to be given by the following formula, where x1, xn are coordinates in G, not in, sorry, in G star, right? Corresponding to the basis E1 through En in G. And C, I, J, K are the structure constants. So if you take this,
How is possible to treat phi
As a bivector, yes.
I forgot to say use this. These are actually components of this bivector. So there's just this. Yeah, only this. I forgotten to write down to give the basis here, right? Okay. In this case, as you see, components are linear in coordinates x1 through xn. So if you take constant vector field, say given by psi k dk, psi k are constants. Real or complex doesn't matter. Then, of course, the condition lambda square of psi applied to pi equal to 0 holds. Yeah, and we can obtain a large family of commutative elements inside S of G.
You take psi here. What do you take psi? You take any.
Yeah, any constant vector field.
Any constant vector.
Any constant vector field, anything. And one can show it is what they call Mishenko-Fomenko conjecture. It's been proved some 15 years ago about, so that in this way one can obtain maximal commutative subalgebras in Poisson algebra S of G. So you not just obtain some commutative subalgebras, you obtain maximal commutative subalgebras in almost all cases. Yeah, polynomials on G star, polynomial functions on G star, precisely. Great. Now, this method first appeared in the end of 1970s, and a bit later, Ernest Borisovich Weinberg asked the following question. Well, take the universal enveloping algebra of G. The universal enveloping algebra. I believe everybody knows what is the universal enveloping algebra of. Sorry?
I hope.
Yeah, I hope so. Of the algebra. Then there is a linear isomorphism. Linear isomorphism. Non-canonical, which is due to non-canonical except for the top degree term, which is due to Poincare-Birkhoff-Witt theorem. Between universal enveloping algebra and the symmetric algebra of G. Now, inside this algebra, you have the maximal commutative algebra induced by the shift of argument method, denoted by A sub psi of G. It is the algebra induced by the shift of the argument. Alongside.
To be
Yeah.
exact, you mean linear isomorphism between vector spaces, not between algebras.
Yes, between vector spaces. I mean, well, if you want, I can explain this a little bit in more details. Actually, well, yeah, there is. You can do the following thing. You take UG. There is filtration induced from the tensor algebra on UG. So filtration is induced by the projection of not more than by the elements in the tensor algebra which are equal to the product of no more than p elements in G, right? Now, if you take the graded algebra associated with this filtration, so this is what they call the graded algebra. I've forgotten to, so there's this summation sign here, right? I'm sorry, you don't have enough space here. So this is a graded algebra, right? Then it is canonically isomorphic with symmetric algebra. On the other hand, for every element f in UG, you can it has filtrate. It has some filtration. That is the maximal, yeah, but the minimal term fp, which contains f, right? Have it. So then f. If you now quotient out filtration p minus 1, you get an element which I will call the symbol of F inside S of G. The map which associates a symbol with every element in universal enveloping algebra is a very nasty map, actually. It is not linear, but it is well defined. So for every element here, we have the top degree, we have this, have its symbol.
This is genius symbol because these are
The top, it's not just the symbols, but a principal symbol.
Yes, yes.
It's a natural, yeah, it is the principal symbol of F. Yeah, so for every element here, we have principal symbol. And now, suppose we have some element phi here. We can find, now the question is if we can find for every element phi in A sub psi, some element phi hat in UG with the same principal symbol, right? Of course.
So what is A sub psi?
In a couple of minutes, I'll recall this. Right? And such that phi hat and psi hat commute in universal enveloping algebra for any phi and psi in A sub psi. So A sub psi is what they call the argument shift algebra. It is the algebra spanned by various derivations of various elements in the center. In the Poisson center of SG. The Poisson center of this algebra is very well known. It is related with the invariant part of the adjoint action of the group on this symmetric algebra. Yeah, this is spanned by invariant polynomials. So the question is how to get something in universal enveloping algebra, which will have the same set of principal symbols, but which will still commute. If you just take some element here and you try to use this identification, which is induced from von-Graeber-Hopf-Witt theorem, then you'll probably fail because this von-Graeber-Hopf-Witt theorem only gives you linear isomorphism of spaces. So finding correct continuation of principal symbols to some elements in universal enveloping algebra, which will commute if the principal symbol commute, is a very interesting question.
It's kind of quantization.
Yes, precisely. So let me continue with what is known about this. Of course, this has been done, so my talk will not be just about the problem, but about something else. So what is known about this? So first, in about 2002, I believe, or 2001, one of students of Weinberg, Tarasov, gave the following, obtained the following theorem, proved the following theorem. Now, before I proceed, I need to say that, repeat the description of the center of the universal enveloping algebra, because I'll need this. So the center of the universal enveloping algebra is actually isomorphic to the center, let's call it Z. Center is isomorphic to the center of S of G. the Poisson center of S of G. Both are spanned by at G invariant polynomials. In G, in SG. Sorry? Well, I think this is classical, totally classical. I think it's been known long before Gelfand was born.
But there was paper by Gelfand in
Not probably before Gelfand was born, but definitely before he became famous.
Well, it stated that this is his result.
Yes?
Yes.
That the center here is isomorphic here?
No. The center consists of G invariant polynomials.
I thought it's been classical and known to
but
Harishchandra at least.
1951 or 52,
Yeah?
something like that.
I thought it was known to. Yeah. I didn't know this. I thought it was proved by Cartan or by somebody else long, but before.
Nevertheless.
Okay. Okay, so knowing who to refer to is an important thing. So anyway, it is known that they are isomorphic. Actually, one can
understand which statement.
the center here and here.
Center is commutative algebra.
Yeah, both, but they are isomorphic. They're isomorphic as algebras. The center here and here, there is an isomorphism of algebras from left to right.
On the right hand.
Yeah.
Right hand side.
So the center here, so there are various ways to explain this. Yeah, precisely. So yeah, the center here is well known. It is given by the collection of polynomials in SG invariant with respect to a joint action, right? And one can show that it is the same case here. The description is the same. There is, however, if you just take a polynomial here, a polynomial f here, and symmetrize it. So I believe everybody knows what is symmetrization map from S of G into universal enveloping algebra of G. Right? If you just take symmetrization of an element here, then the problem is that this is not equal to no, from here to here. From right to left, you want to get it from right to left. It is, I don't think there is a canonical way to get this map from right to left. I don't even believe there is a canonical way. From left to right, there is symmetrization, right? Yeah. So if you take this map, this symmetrization, it will not be equal to this. So this symmetrization gives you actually just the linear isomorphism of these spaces. However, there is a way to improve this map to get an isomorphism of algebras. It is what they call the Duflo map. I'm not going to speak about this. So if you add some correction terms to this symmetrization map, you will get an isomorphism of algebras from left to right. But in any case, one can describe the generators of this center and of this center as well. Yeah.
I repeat, this isomorphism is trivial because we have two commutative algebras. So what does it mean with statement?
But they may have the different number of
Generators, different dimensions and different, yeah.
Dimension, it is evident is the same.
No, it is not.
No, not evident at all. Well, actually, it's not difficult to show that it is that they are the same. Yeah, it's not totally trivial. It's not very hard to show, but it is not trivial. And especially constructing this isomorphism, Duflo isomorphism is totally non-trivial. That's really hard. Duflo isomorphism is hard. Okay, but if you know the generators, then you can actually obtain non-canonical isomorphism. Duflo isomorphism is canonical in some sense. It doesn't depend on any choices. It is given by some canonical formula. But if you choose generators, then you get some non-canonical isomorphism, for instance. So generators of centers for G equal to GLN.
Sorry, just to recall, this is morphism. I'm sorry to ask you so many questions. Is it related with the problem of Casimir's for difference for physics mathematicians? Because I know that for Casimir's for us it is one thing, for mathematicians.
I don't know what Casimir's are for you. I don't know. I'm not sure I know this.
Okay, sorry.
Okay. Okay, so generators of the centers for, say, GLN are well known. So there are two sets of generators. So the first set, there's several sets of generators, but there are two canonical sets which are best known. The first set is given by is equal to the coefficients of the universal characteristic polynomial. Let Lij be the generators of the Lie algebra GLN, right? So they play the role of matrix units. Then you can form a matrix L of these elements. Now you can regard these elements as subspace, as elements in the symmetric algebra of GLN. And you can take determinant of L minus lambda times identity. This is characteristic polynomial of the universal matrix L, and you decompose it as the series in formal parameter L lambda. And now these polynomials in Lij's give you the one set of generators in the center of GLN.
But it is a very important remark that necessary to compose the matrix L special way. You have generator of GLN, and finally you should put with generator special way ABCD.
I mean, yeah, of course, Lij stands at the ijth place of this matrix. Definitely.
Present here the commuter, the bracket between two generators.
Sorry?
And finally, consider please the simplest example of dimension 2, ABCD.
Right.
So
You're supposed to help me. Okay, so n equal to 2, and you have this matrix A, B, C, D, and you take minus lambda. So when you take determinant, it will equal to A D minus.
what is commutator between A and B?
What kind of commutator? I mean the Poisson bracket? The Poisson bracket? Oh, sorry, I didn't think it was really important at this moment. Yeah, sure. We use the following commutation relation. For me, it is like this: Lij commutation with Leq will be equal to delta IQ Ljp minus delta Jp Liq.
Okay, ABCD is the simplest example. Could you present it explicitly? So my remark is the following. So
Yeah.
if you consider the matrix composed from 4 elements, it's very important that A bracket with B is equal B, A with C is equal minus C, and so on. If you compose another matrix by transposing B, C, you have another matrix composed from generators of the universal enveloping.
I'm not working in universal enveloping algebra. I'm still working in symmetric algebra, so it doesn't matter much.
Finally, it's very
Eventually, it
important.
will be important, but not now. And for the moment, I'm working in symmetric algebra. But yeah, it is probably yeah, illuminating to write down this commutation relation in terms of A, B, C, D. It's not. Yeah, sure. So may I erase this? Yeah. So now if you write down these formulas, you'll get some explicit expressions for sigmas. And the first set of generators is given by sigma 1 through sigma n in S of GLN. But then the symmetrization map, that is a good result that it will give you elements sigma 1 hat, sigma n hat, elements in the center of universal enveloping algebra, and this will also give you generators of this center. Okay. And another set of generators, also quite important and interesting. It's probably simpler than the first one in some respect, but in many respects it's worse than this. And this one, it is the following. So the second set is given by, so you take the same matrix L, you take its powers and take the traces of these powers. It's again a polynomial in SG Ln. And in this case, you don't even need to symmetrize it. If you just take the same algebra, the same matrix, but you look at it as a matrix in the matrices with coefficients in GLN, and take the same formula, it will give you elements in the center of universal enveloping algebra of GLN, and it'll also give you, it'll also be generators. So this is another set of generators. Probably this is the Gelfand's result, which you implied it. Probably this was. Okay. So now I'm going back to Tarasov's result. And his result was as follows, was the following. You take elements sigma 1 through sigma n in the center, in the Poisson center of symmetric algebra of GLN. Take psi, a constant vector field on GLN star. Take psi to the power p and apply it to some sigma k, and then symmetrize what you obtain. And with some work, actually with quite a lot of work, he proved that elements of this sort will always commute. It is not at all trivial because, as you know, symmetrization is not a homomorphism. So if you just take elements in the center, they will definitely commute. But when you go away from the center, what happens to the commutation is not at all evident. So he proved this by very lengthy calculations in explicit coordinates in universal enveloping algebra. Later, Leonid Rybnikov gave another construction of such algebras. So observe that this construction just gives you a set of generators in universal enveloping algebra, just give you a set of elements which commute with each other in universal enveloping algebra. What happens with symmetrizers of psi p of some other elements f in the center of SGLN is totally not clear. So what happens with these elements, you cannot guess it from this formula at all. It is a total mess. So in other,
So this is too only for these
yeah,
specific generators.
yeah, yes. So what happens to other elements is not clear at all. Another construction, very similar to this, but with more general Lie algebra, was suggested by Leonid Rybnikov in 2007 or something about this. I'm not going to go into details into this construction, but well, roughly speaking, he observed that for any Lie algebra, any semi-simple Lie algebra, G, one can construct what they call the Katz-Moody algebra, G hat. It's a fine version of this Lie algebra with some central extension taken. And then you take universal enveloping algebra of this infinite dimensional Lie algebra, Katz-Moody. And you set the central element in this construction to be equal to a certain number, what they call the critical level. So you just set critical level. And in this case, it turns out that this universal enveloping algebra has a very large center. This center, as far as I can remember, is generated by something called Sugawara operators. And if you take now this center and use certain evaluation morphism, this center will give you a large commutative subalgebra in UG. So find an explicit elements which are obtained by this construction is extremely difficult question. It's been studied by Moliv and his disciples in the last 10 years. I believe they know how to do this in most cases in some classical, for classical.
Does the construction also use the argument shift or not?
Actually, this the evaluation, there is an argument shift which is inside this evaluation morphism, evaluation map. The way you define it involves the shift. No, unfortunately, no.
Because you say that it was done by Stanford.
Yes, it's very by brute force, what I would say, what I would call. It's been done by brute.
There is no explanation.
I mean, brute force computation, only that. And the way Rybnikov defines evaluation morphism, I don't remember it. It's something like you take coproduct first, then you take the projection on one leg and some morphism into symmetric algebra on the other leg, and then you take evaluation of the symmetric algebra and so on. But yeah, no more than that. this really involved. And the problem of, and the reason why it is involved, I believe, is that actually these elements which constitute the center on the critical level of Kac-Moody algebra, they are really not well understood. They just exist, as much as I can remember. That's what Leonid explained me. So now I'm going to suggest some not probably very new, but at least to me it is new, some other method of obtaining some commutative subalgebras inside the universal enveloping algebra. I must warn you from the very beginning that I cannot prove that this method will always give you commutative subalgebras in this way. I have some partial results which show that this happens in many cases, but I cannot prove that it will happens always. We begin, I will deal only with the universal enveloping algebra of GLN. So first, I'll introduce what I would call quasi-differentiations of universal enveloping algebra. Namely, I'll introduce following the works of Dmitrievich and Pasha Saponov, and use the following set of operators: Dij on UGLN. They are linear operators, and they verify the following set of conditions. First, they kill the scalars. Second, on generators, they are given by the natural formula. So they are given by the Kronecker deltas. But the most important part is the third part. It is the very modified Leibniz rule. Dij applied to Fg should be equal to Dij F times G plus F Dij G. But also there is a third term, which will look like IKF dkjg. The summation over k is understood here. It is remarkable that these operations are well defined. And to prove this, you first check that this Leibniz rule is actually co-associative. That is to say, if you apply it to a triple product, then the final result you obtain will not depend on the way you put parentheses here. Right? So you can define, you can extend, you can use this formula to extend this operation to the tensor algebra. Right? And then you check that Dij of the commutation relation L AB LCD minus LCD LAB minus LAB LCD is equal to 0. So it means that now the ideal which generates the universal enveloping algebra is mapped by these operations into itself. So it is well defined. This operation is well defined. Now take arbitrary constant metrics. And you form the operation d sub psi equal to the linear combination of these operators dij with coefficients psi ij. Then, yeah, this is constants. 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 So what the main conjecture of this talk is that for any two elements in the center, for any two elements of G in the center of universal enveloping algebra, and for any two non-negative constant well, natural numbers, integer numbers, P and Q, d sub psi applied P times to F will commute with d sub psi applied Q times to G. Is conjecture. And now I say a few words about what evidence we have that this conjecture holds. So first, Pavel Saponov, who is not here because he has some family reasons, proved by straightforward computations with formulas for sigma k that if F and G are equal to some sigma p, sigma k, sigma L, then this holds, this condition holds. Yeah, symmetrized, probably had. Yeah, symmetrized coefficients of the universal characteristic polynomial. Well, unfortunately, this is not enough to prove the theorem, because the Leibniz rule has this nasty third part, and this third part is well, it spoils the whole thing. If you just apply this operator dxi to a product of two elements, you will not obtain something expressible in terms of its applications to the factors. You see? So unfortunately, if we try to choose, if we take f equal to the trace of L to the power p, and so probably k, and trace and G equal to trace L to the power L, then we cannot use this result to prove that they commute. However, if K and L are less or equal to, say, 5, I believe, right? Yasushi, I think you did this up to degree 5. By the straightforward computations, you can show that this also holds. You can also try several examples with well, they really take some space. One more evidence that it is true. If P and Q are equal to 1 or 0, 0 is not interesting because 0 will preserve elements in the center. Yeah, so it's not interesting. But if you take P and Q equal to 1, then it is true. Then for every F and G, it holds. So I'll explain how this can be proved in a couple of very briefly, because again it involves some rather nasty computations. It involves, so the first thing you do, you consider Dij applied to the trace of L to the power P, some P. You can do it inductively. And you show that if you take the matrix of this sort, where this partial derivative, quasi-derivative, stands at the space, at the place ij, then it will be equal to a polynomial in matrix L. So you take matrix L, it is matrix with coefficients in UGLN. So this is an algebra, so you can obtain polynomials in this with this variable with coefficients in the center of UGLN. That's what you do. So you can do this by induction. Now, if you take,
Is it to prove or not? Why?
Sorry?
Is it easy to prove?
Not quite actually. It's not very hard actually. If you do some exercises with first few terms, you'll see the general pattern there. You'll see the general pattern. Actually, if you probably it's even better to begin with something like Dij L to the power P AB, something like this. Probably it's even better to begin with this. In this case, you really have some straightforward way to write down the induction. All right. Then, so it follows that d sub psi applied to this trace LP will be equal to the following thing. You take trace, so it will be equal to the linear combination of the following form. You take the coefficients, you take elements in the center. AK is in the center, are in the center of universal enveloping algebra. And then I take the following thing, take trace of L to the power K multiplied by the matrix psi and take the trace of this. Yes, this particular psi. This particular psi, which the one which determined this separator. Moreover, yeah, and now the second step is to show that commutator of these two elements it vanishes. This is also done by induction. To this end, you need to know the commutator of LPAB with LQCD. You can obtain this formula by induction again. It is expressible in terms of powers with lower degrees. For instance, if, say, p is equal to 1, it is equal to delta AD LQ BC minus vice versa, delta CB LQ AD. And so on. We go on, and you obtain some formula for this. And then you take a trace and you show that it vanishes. And eventually, if you want to prove that for any element in the center, any two elements in the center, this vanishes, you do the following thing. You take F times G, for instance, you can commute it with H, right? Take d psi, and then this is equal to d psi F times G H plus F d psi G H. So this is equal to 0 because everything commutes. But then in the end, you'll have the following thing. You'll have so the third term in the Leibniz rule is equal to d I j f d gj kg, right? So times psi I k. Yeah, this is a trace, right? But this is equal to the product of the matrix Dij f with the matrix Dkg G. So this matrix has the form of this sort, right? Is a polynomial in these coefficients, right? I think I have erased this already. So it's a polynomial in matrix L with coefficients in the center. And the second element, the second matrix, the second element, the second matrix is also of the same form. So their product also has the same form, and we come back to the same identity as before. We need to prove that these two elements commute. So eventually we get the result for any f and g. Okay, so that's as much as I can say, and now I want to give some, how do you call this? In Russian, it's called сеанс черной магии с полным его разоблачением. I want to explain some very simple combinatorics which is behind these quasi derivations, if you allow me.
Yeah, for sure.
So if somebody can prove this in general, I'll be pretty happy. So far, there are too much evidence that this conjecture should be true. Too much evidence just to assume that it is all by some chance. But the complete proof is not quite clear. And on the other hand, the combinatoric which is behind this quasi-derivation is very simple. Consider the operator theta. So we already considered the matrices Dij of F inside matrix with coefficients in UGLN. So let us consider one more matrix. Theta of F equal to F times the identity matrix, plus this one. Let us call it D of F. Then theta of F times G is equal to theta of F times theta of G. And it follows directly from the Leibniz rule. So this is a homomorphism. And it turns out that this homomorphism is extremely simple. So what kind of homomorphism is this? It is this. Theta of F is actually equal to the following thing. You take F, take the coproduct in universal enveloping algebra. You land into the tensor square of universal enveloping algebra in this way. Then you apply the canonical representation of universal enveloping algebra, in which you just identify elements in GLN in Lie algebra with matrices, and that's all. So you end up precisely here in matrices. And I claim that it is the same. And the proof is pretty simple. This is again a homomorphism of two algebras. So just if you want to compare this homomorphism with this homomorphism, you only need to do it on generators. And on generators, it's straightforward. We just get the same result here and here. Yeah. Actually, there is derivation. If you just subtract one, if you just subtract the top degree element, you obtain some the derivation. You restore it. Just this. Yeah, just one more step. Just a bit further. So now, comparing this formula with this formula, we see that d psi of F commutes with d psi, so dp psi, dq psi of G, if and only if, well, for all P and Q, if and only if trace of psi. So let's denote by theta sub psi of F the following construction. Theta sub psi of F is equal to the trace of psi times theta of F. And big psi, this is big psi. Yeah, we just take this constant matrix psi, multiply it by the matrix theta of F, and take the trace. And this is again operation from universal enveloping algebra into itself, well defined. There is almost no difference between this and this operation, almost none. So it's no wonder that this commutator is equal to 0 if and only if this commutator is equal to 0. Right? Great. Now, this iteration of theta sub psi can be written in a very simple way. You take p times co-multiplication of f take p times the representation rho, tensor power, of course. Take psi p times and take the trace of this matrix in the first p coordinates. So the last coordinate is just element in the universal enveloping algebra. So you just take the trace in all first p coordinates. Now an element here vanishes. An element in universal enveloping algebra vanishes if and only if its representation vanishes for all tautological, all representations of GLN. So what representations there are in GLN? There is one canonical, but you can also take tensor powers of this canonical representation. So if you take a k times, then it should be like this. So some element vanishes if and only if this representation vanishes, right?
Is C essential?
No, it is not. It actually can be real numbers or any other. It's pure combinatorics now.
It's not clear. Universal algebra in power k.
When I say, I mean, you take k times co-multiplication, k-fold co-multiplication.
Communication here is presented.
I just omit it because actually you just do the following thing. You just do UGLN, take k times co-multiplication, and then apply rho k times. So these representations actually, as far as I can remember, these representations contain all irreducible representations of universal enveloping algebra. And it is easy to show that an element here vanishes if and only in all these representations vanish. It's not hard to see. Now, if you take this formula and apply this kind of representation, you'll see that the only difference will be that you now put rho here as many times as you want. Right? So that's what you get. This is an operator. In M-fold tensor product of matrices M by N matrices over C. And it is easy, it's actually known that this representation, I think, sorry, even this representation, this element, well, what is it equal to? Because when F is in the center, its coproduct, when you take representation, will commute with all symmetric matrices. So it will be equal to an element in the center of the permutation group. So this is an element in the center of permutation group in P plus M elements. I mean, not in the center of permutation group, but in the center of the group algebra of the permutation groups. You have an element in the center of the group algebra. This center is well known. So let's denote this element by P sub W. And now the question is it true that for all elements P sub W, P sub U in the center, trace of this form and with U as well will commute?
I don't understand who are these guys, U and W.
So it depends on how you describe the center in the group algebra of the permutation group. Actually, one can show that the center is equal to the averaging operators over conjugation classes of elements in the group. So if W is an element in the group of permutations, you take it conjugation class, and then you take the averaging operator, the sum of all elements in this conjugation class, divided by the number of elements.
It is very combinatorial.
Hmm?
It is where you say, when you say.
In my opinion, it's very combinatorial because description of the commutative subalgebras in the group algebra of permutation groups is a combinatoric problem. When I was preparing for this talk, I ran across a paper by Varchenko, Tarasov, and I forgot what was the third name. And they suggested something very, very close to this. The only probably Muhin, yeah, Muhin, where they suggested something they called beta algebras in these group algebras, which are commutative. The only difference was that they didn't consider these coefficient metrics at all. They just considered these traces without any coefficients, but then they added some coefficients inside this universal development, inside this algebra of permutation of the group algebra, inside the group algebra. Yeah. So you see, the results we already know, for instance, results by Saponov and results which I described for the first derivation, they show that these operators actually commute for some particular choice of elements in the center, for instance. For instance, if f is equal to the generators equal to the coefficients of the characteristic polynomial, yes, then these elements will always commute. So this gives you some interesting subalgebra, commutative subalgebra in the group algebra of almost in the group algebra, because there is this psi again. So I think it's interesting.
Well, if we compare two problems, GLN and SON.
Yeah, as far as SON,
which is more difficult?
I have no idea, because actually, if
for SON,
yeah, I spoke about this theta operator, just because you see this theta operator is easily extended to any Lie algebra, to arbitrary Lie algebra. There's no need to work with with the GLN. You can do it for any Lie algebra, and all the constructions here go word by word there, and you obtain some elements. But this time, I think it's not necessary the permutation group. I don't know. I don't think that it will be simpler with SON. Yasushi did some computation with very low degrees like SO4, which showed that in that case, the existing elements in the center, if you derive them in this direction, they actually commute. But I don't think it's really very, very hard, because these elements are quadratic. So when you just take their derivation by their quasi derivation, the only surviving elements will be equal just to the elements will be linear. And on linear elements, the commutators will be equal to the Poisson bracket. And we know that the Poisson bracket is equal to 0. So there is some evidence that, so you can regard this as an evidence that this actually works, but in the SON case. But this evidence is definitely not sufficient yet. Okay, that's all.
Okay. Now I need this device.
Yeah, sure. I think I need to turn it off.
No, it works. So, questions, remarks?
May I ask a question, Yosef?
Yes, of course, but
Женя Ферапонт.
Женя Ферапонт.
Здравствуйте. Yeah, sure. Sure. Sure, I will be glad to answer if I can.
Right. Thank you very much first for a very nice talk. Can you hear me?
Yes, I can hear you very
So
well.
thank you very much for your talk. I have a simple question. So you described this quantization procedure from S of G to U of G, right?
Well, I described it very vaguely, I'd say.
Yeah, but still, my question is, are there examples when there are two different quantizations, non-equivalent, or there is a uniqueness theorem? There are two things, existence and uniqueness, right? Are there examples when it is non-unique?
Well, in this general setting, there are definitely lots of examples. For instance, as far as I can remember, if you quantize symplectic manifold, then it is known that there are as many different quantizations as many elements in the second cohomology there are. Even more than that, you need to take second cohomology with formal coefficients in some formal variable.
No, but when we take your construction, you have Lie algebra.
It's not my construction, actually. Don't say it's my construction. I'm only saying that I just want to justify the question. We are looking for some way to raise a commutative algebra in the Poisson algebra to a commutative algebra in symmetric, in universal enveloping algebra. If you want a more canonical way to do so, I can describe it. There is a more canonical. I didn't explain it here, but I think if you want some more canonical description, then you need to introduce formal parameter. It is traditionally denoted by h bar. You take S of G, take h bar. You also consider universal enveloping algebra with h bar in it. So it's actually the same as the usual universal enveloping algebra, but the relation is not xy minus yx equal to the commutator, but this should be equal to h times commutator. So you consider this. And of course, you allow now formal power series with h in it. So now there is the symmetrization. Symmetrization now gives an isomorphism here to here. And you pull the product here to a star product on the left. And now, there is a map which sends h to 0. And as you see, this is a homomorphism now from this algebra to this algebra. And if you want, the most canonical way to put this problem is to whether there is, suppose you have an element f in SG and an element G there, and you know that the Poisson bracket vanishes, then the question is if you can find f plus h bar f1 plus and so on, and G with the same tail behind it, so that they will commute with respect to the star product. So that's probably the most canonical way to formulate this problem, in my opinion, at least. So I don't know how to do this canonical way without h. In this case, if you fix the second term here, then as far as I can remember, this quantization is unique.
Mhm.
So probably the answer to the question is also that it's unique. In general situation, when you have a non-trivial manifold with some cohomology in degree 2, you usually have not just one way to quantize, but you have many different ways to quantize, and these different quantizations are parameterized by the elements in the second cohomology group, naturally.
Mhm.
Well,
Thank you.
cohomology group, yeah. You're welcome.
Zhenya, are you satisfied?
Yeah. Thank you very much.
More questions? Well, no, thank you very much. Gosha, thanks a lot. It was very nice and interesting. So we next Wednesday, same time, and everyone is welcome. Thank you for participating, and goodbye.
Thank you. Okay, now I turn it off.